Why do we need a query optimizer? What does it do exactly? How does the optimizer enumerate different plans? How many plans can it come up with? And how does it choose between these plans? These are all questions that I've got from folks, and I've got lots of requests to talk about the optimizer in detail. So today, if you are curious to know how the optimizer works, this is the video for you, so stay tuned. Hello and welcome. My name is Elhelw. In a recent video, I talked about the SQL query lifecycle and the different steps that it goes through from submitting it to the system until we get the results. Particularly, we talked about how it starts with the parser, where it looks at the query, splits it into different tokens, does some syntax checks on those tokens to make sure that the query is written correctly, also checks whether all the items that are mentioned in the query, like table names or column names, are all actually existing objects in the catalog. And then once we're done with that, it creates an initial query plan. This initial query plan goes through the optimizer. The optimizer is then able to come up with other alternative plans and then figure out what the best plan is. This best plan is then taken to the execution engine, which starts executing all the operations of this plan on the data to give us the result that we're looking for. So today we are going to talk specifically about the query optimizer and get into details. This is going to be a longer video than usual, and it will have a lot of information, so brace yourselves for a ton of information there, and hopefully it's not too complex. I'll try to simplify it as much as possible. One thing to note, when I talk about query optimization, when we're talking about it today, we're talking about the query optimizer component that is part of the database management system, specifically part of the query engine. This is a component that automatically gets called with every query to optimize the query and come up with the best execution plan. This is different than when some folks talk about query optimization as something a programmer or someone would do to their query before submitting it to the database system. Like they can rewrite the query in different ways to try to help the DBMS to run this query fast. So this is a different kind of optimization. This is called like query tuning or performance tuning or something like that. But here today, I'm going to be talking about the internal query optimizer. So just something to keep in mind. Okay, with that out of the way, why do we need the query optimizer in the first place? To best answer that, let's start with an example. So suppose we have an employee table that has all these different fields. Let's assume that this table contains 5,000 rows split over 500 data pages, so roughly 10 rows per page. Also assume that we have an index on the department ID column. We have another table, department, that has also a bunch of attributes, and let's say it has 100 rows in 10 pages, so again, roughly 10 rows per page. And let's suppose that we have an index on the name attribute. Now with those two tables, we have a query that says select name and salary from employee join department on department ID, also where the department name is sales. Okay, so with this query, one possible plan to execute this query would be something like this. Remember, for query plans, we usually start from the bottom up. So the bottom is the inputs, and then the data flows from each node to its parent. So here we have both table scans. We have a nested loop join that will join those two tables, apply the additional filter on the department name, and then project the columns that we are looking for. So this is one way to run this query. If we use this plan, let's try to estimate the cost of this plan. And I'm going to use a very simplified cost method here. I'm going to say just the cost is the number of page IOs that we're doing, right? Of course, in reality, the cost will involve a lot more other things like, CPU, potentially memory, stuff like that. But let's just focus on one thing for simplicity. So here, the nested loop join is going to read from the outer side, and then for each page is going to read the inner side. So the outer side here has 500 pages, the inner side has 10 pages. So this is the formula that we have. So this is all the reading that we're going to do. So suppose that the total cost here is 5,500 page reads. This is for the plan that we have here. Now we could change this plan, right? One thing we can do is that we could switch the inputs of the join. So now the department is on the outer side and the employee is on the inner side. And with this new plan, now the cost changes, because now the outer side has only 10 pages, so the cost becomes 5,010 page reads. So it's slightly less than before, which is something that we have mentioned when we talked about the join. We said that we should always try to make the smaller table on the outer side, right? Because it will affect the cost of the query. So this is a second plan. We could come up with different plans as well. Look, one other thing we can do is that we could potentially push the filter to happen before the join, right? When we push something down in the plan, it means it happens earlier. So now we're filtering the records before they go to the join. So now the select node is going to read all the 10 pages, do the filtering. This will end up with just one row. And then for that row, we're going to read all the inner side, which is the 500 pages. So now we have read a total of 510 pages. So this is a completely different cost from what we've seen before, because we've changed the plan as well. So far, we have not taken advantage of the indexes that we have. So if we try to use the indexes on both sides, we could use the index on the department side to look up the sales department. And we could also use the index on the employee side to make this into an index nested loop join. So in this case, it will look something like this. I'm using some just random numbers here for the index costs, which is going to be definitely much less than doing a full table scan, but it's going to be roughly around this number of reads. So 57, 60 reads total. These are all equivalent plans. They will all give us the same result, but each plan has a completely different cost. Choosing which plan to use eventually is the challenge, is the reason why we need the optimizer. The exercise that I did right now of coming up with different plans, estimating the cost of each plan and then choosing one of them, this is basically what the optimizer does, except it does it on a much larger scale because it has way more plans to consider and it has more complicated cost functions to compute. On a very high level, the optimizer has two tasks or two main responsibilities. One is plan enumeration, which means coming up with these alternative plans. And the second is comparing these plans and coming up with the best one. Comparing them could be based on heuristics or based on cost estimation. So those are the two tasks on high level. Let's talk about each of them. Let's start with plan enumeration. So plan enumeration, like I said, it means finding all these equivalent plans to the one that we started with. Let's talk about plans. We may have mentioned that before. The plan that we've seen, that tree shape plan, this is basically a tree representation of a relational algebra expression. The relational algebra expression that's equivalent to the query that we wrote. There might be multiple plans. The plan tells us basically how to run the query. Like these are the operations that we have. We have these table scans, we have a join, we have a filter, and so on. So these are the operations that we need to execute. And the plan tells us the order in which to execute them. And because SQL is a declarative language, not a procedural language, we might have different plans that are equivalent with different operations or different order of executing these operations. Each node in the plan is an operation. Like join is an operation, scan is an operation, select, project, all these are different operations. Some of the operations might be logical, some of them might be physical. A logical operation or a logical node in the plan is something abstract or conceptual. It is not something that we can shape to the execution engine. It is something that represents an operation in relational algebra. For example, join, selection, projection, all of these are abstract or conceptual or logical operations. And when we talk about join, for example, like here we said that join, we understand what the join means. We understand if we have these two things being joined, the output will look like this. The logical join does not tell us which join algorithm we're using. It just tells us this is a join operation, we're joining based on this column or this condition. Same thing that goes for aggregation. Again, we understand what aggregation means, but the logical node or the logical operation does not tell us what algorithm we're using. This is something just the semantics of the operation. On the flip side, the physical node is the actual implementation or the concrete version that has an algorithm behind it, which we can actually execute. So when we talk about nested loop join or hash join or merge join, these are concrete implementations of the abstract of the logical join operation. So these are physical operations. These have a cost. The nested loop join has a cost that's different from the cost of a hash join. But they all have the same join semantics, so that's why there is a logical join that encompasses all of these together. Same thing for aggregation. You have hash-based aggregation, you have stored-based aggregation, which we have talked about in a previous video as well. All of these have the same semantics. Both of them will produce the same output, but they do it in a different way, and therefore they have a different cost. These are the things that we can actually execute. They have a code that you can run. So why are we talking about logical and physical nodes? When we start with the query engine, after parsing the query, we end up with a plan, right? This plan is usually logical. This is just a representation of the query in a relational algebra form, and it only has the logical operations. We cannot execute that logical plan. We need to transform that logical plan to a physical plan, and then that physical plan needs to be executed in the execution engine. So one of the jobs of the optimizer, as it's doing in the plan enumeration and costing, it's also transforming that logical plan to a physical plan. Now, as we're talking about plan enumeration, right? We have seen in the example that when we've changed, for example, from nested loop join to hash join or a different kind of join, that gives us a different plan with a different cost. So just by changing the join algorithm, you get a different plan. Also, by changing the join order, like flipping both sides of the join, that gives us a different plan. So each small change gives us a different plan with a different cost. The more things that we can change, let's say we have multiple joins, or we have different aggregations, or different filters that we can push down or push up, the more things that we can change, it means that the space of the plans gets much bigger. It gets exponentially bigger with the size of the query. So for a large query, this plan space, the number of possible plans that we can consider, becomes so big that it's very difficult or even almost impossible for an optimizer to try considering all of them and estimating the cost for all of them. Because it will be ridiculous for an optimizer to spend an hour going through all the different possible plans, trying to estimate the cost for all of them, and then choose one of them for only that plan to take 5 seconds to run. So the optimizer needs to limit the number of plans that it actually looks at, that it compares, in order to come up with the best plan. So a smart optimizer needs to find a subset of plans where this subset contains like the most efficient plans that it can deal with. So anything that is obviously a bad plan should be excluded very early on. How do we eliminate the bad plans early on? The optimizer usually does this in one of two ways, or maybe a combination of both. There is a rule-based optimization, so this is based on some heuristics. There's some heuristic rules that it applies, and it tells the optimizer which plans it should exclude. And then once it's done with that, then there's a cost-based optimization element as well, where it can estimate and compare the costs for different plans and decide which ones to keep and which ones to eliminate. So let's talk about both the rule-based and the cost-based optimization steps. Starting with the rule-based optimization. Rule-based optimization, like I said, this is a bunch of heuristics that we have that feed into transformation rules. What does that mean? It means that let's start with any given plan. We look for a pattern in the plan. And if we find that pattern, we apply a transformation to get an equivalent plan. And we know based in heuristics that the second plan, the new one, is going to be better than the old one. And we do this without looking at the data, without looking at the costs, without anything like that. We just know that this transformation is always going to give us a better plan. These transformations are designed to get rid of the obviously bad plans. So the assumption is that each of these transformations, the new plan is definitely going to be better than the old one. So you can see that as like a safe transformation, or just like a very obvious choice that you have to always use the new one. And the one that's eliminated, it doesn't eliminate one plan, it eliminates a whole class of plans. For example, when we did the filter pushdown, right? This is the example that we're looking at right now. So let's say we start with a plan like this. We have a filter selection on top of a join on top of A and B. So one of these transformation rules will say, look for that pattern, that filter on top of a join. This is the pattern that we're looking for. And by the way, this is equivalent to a relational algebra expression. So it's equivalent to something like this that has a selection on top of a join. In relational algebra world, you have also some equivalence of expressions. So this expression is equivalent to another expression that applies the selection only on A and then joins the result with B, instead of doing the join first and then applying the selection. So in that same sense, if we represent this in tree form, the plan would look like this. This is a safe transformation. We know that when we push the filter down the plan, means that we apply this filter earlier on, then we eliminate a lot of rows. So we only have much fewer rows to go into the join. So the cost of the join becomes much less. So this is always going to be the case. Like the filter will never end up producing more rows, for example. So this means that we did not only eliminate that first plan, we eliminated a lot of plans that have the filter on top of the join. So these plans might be, A join B with a filter on top, B join A with a filter on top, and then the join could be a nested loop join or hash join and so on. So there's a whole bunch of, like a family of plans that got eliminated by this transformation. So this is what we mean by heuristics that help us eliminate the bad plans. So once I make this transformation, I will never consider this plan anymore or any derivative plan of that. So now I have this new plan, and then I can proceed from there. Like I said, this plan is based on a relational algebra transformation. I'm not going to list all the different relational algebra transformations here, but I am adding a link where you can look at some of these transformations. This is a link on the Postgres website. They have listed a bunch of these transformations that are used in the Postgres optimizer. There are other transformations as well that are not relational algebra related. For example, there are transformations that help us simplify some expressions. For example, if you have a selection, like a filter, with a condition like this, x is greater than 5 plus 20. If we keep it this way, this means that for every row where we apply this filter, we have to evaluate this arithmetic expression. And this expression might be, arbitrarily large. So instead of doing that, we can simplify the plan to something like this, x is greater than 25. So we execute that expression once and then store the result. This time we don't have to evaluate this with every row. This simplifies the plan and it makes it cheaper to execute. Another thing, something like this, if we have a greater than 10 and a greater than 50, we can simplify this to just a greater than 50. If a is greater than 50, then it implies that it's also greater than 10. So the a greater than 10 is useless to have. It's redundant. Again, this saves us the cost of having to evaluate this extra condition for every row. So some of these simplifications just reduce the cost. Some of them may actually help us do other transformations later on. If we have something like this that says a is greater than 10 or a is less than 20, well, these two conditions together, they pretty much cover the entire numerical range. So this or means that any value of a would satisfy this condition. So it's like saying select true. So it's like a true condition, which means basically that we don't have any filter. So we could remove this select node entirely and have whatever its input, directly outputting its results. The opposite of that, if we have a filter like this where a plus 2 is null. Suppose we have information in the catalog, in the table definition, that says that this attribute a is defined as not null, which means that this expression or this condition is never going to be satisfied. So this can be replaced with select false. So basically, nothing is ever going to pass through this filter node. Why do we want to simplify this? Because this might actually enable other transformations later on, as we were going to see right now. So another transformation is empty subtree elimination. If we have a plan like this that has a union with two inputs, and one of the inputs has a select false. So this means that this left branch on top of A, nothing is ever going to satisfy this row, so this is going to produce 0 rows from this side. So we can replace this with just like a no-op operation that produces empty results. We can do a further transformation even, so a union of B and something that produces 0 results is basically just B. So we can simplify the plan in different ways. The more we simplify the plan means that we're dealing with a smaller plan, means that the plan space also shrinks. We agree that like the plan space grows exponentially with the plan size, so the smaller plan that we have, the fewer plans that we have to consider. Another example that goes under subtree elimination, this one might not be as obvious as the first one. Here we have another join on top of two tables, but we have a selection in each table. One says that A is less than 10, the other says that B, coming from the other side, is greater than 100. And then the join condition is A equals to B. this join condition is never going to be satisfied because the two ranges, the range of A and the ranges of B, are disjoint. There is no value that exists on both sides that will merge or that will match. So this entire join is going to produce 0 rows. So we can replace this whole thing with a no-op node, and then whatever is on top of that, this might enable further transformations as well. So as I was explaining those, one thing I mentioned is that some transformations may enable other transformations, right? So basically what happens is that we apply these transformation rules one after the other. So given the initial plan, we're going to transform it to something else given one rule, and then on that new plan we're going to see what other rules may apply. Again, like each rule has a pattern that we're looking for. If we find the pattern, then we apply the transformation. This will give us a new plan. In this new plan, again, we're going to check what other rules may apply on that plan. So all the rules are applied one after the other until we finish all of them. But even when we apply all of them, that last plan that we have now might be eligible for some rules that may not have been applied before, or now the plan, we might find patterns that were not there before because we did some simplification, because we did some, let's say, pushing down of filters, or we changed the order of some operations and so on. So we might be able to apply more transformations. So we might have to repeat that process a couple of times until we reach a point where we cannot apply any more transformations. This is usually known as a fixed point transformation, until we reach that fixed point where we cannot transform the plan anymore. In some systems, also because getting to that point might take a lot of time, some systems maybe impose a maximum number of iterations. Let's say we will do this whole loop maybe a maximum of 5 times. So if we did not reach fixed point within these 5 times, we're going to stop, and move on to whatever we need to do after that. So this is also another thing that some optimizers do. All right, so once we reach that fixed point where we cannot apply any more transformations, or we said that we've done enough and we want to move on to the next step. The next step is usually the cost-based optimization. Why do we need that step, or what does it do? In this step, we still may apply more transformations, but we do not have safe or obvious transformations to do anymore. We don't have something that is always better than something else. We can do transformations that generate new plans, but the new plans may or may not be better than the old ones depending on the data. Some instances, the new plan will be better. In some other instances, the old plan might be better. So we cannot just blindly eliminate the old plan. We need to have a different way of comparing them. And this is where the cost comes in. This step also produces both physical and logical plans. The earlier one, the rule-based or the heuristic-based transformations, only works usually on the logical side of things. So all the transformations happen on the logical plans. Once this is done, then we can start looking at the physical ones. And the physical one, as we mentioned earlier, physical plans have a cost element associated with them. So in order to start talking about costs, we need to know what algorithm we're using. So we need to get into the physical plans. So an example would be if we start from a logical plan like this is a logical join on top of 2 tables. So one transformation could be, okay, transform the 2 sides of the join. This is transformation that is not always good. It might be better to have A on the outer side, or it might be better to have B on the outer side, depending on the data, depending on the size of A and B. So this is something that we cannot just say it's always the case. We have to look at the size because the size affects the cost. And then we can also do more transformations to start generating physical plans, because at this point, we cannot estimate the cost. We don't know what kind of join we're using. So we can say, okay, for that first one, we can replace it with a nested loop join. Or we can also replace it with a hash join, or other kinds of join that we have, merge join, for example. So now we can start talking about the cost. And the same thing applies for the second plan, for the one that has B first. We can start generating physical joins, like nested loop join, hash join, and so on. After we have these, then we can look at the cost for each of these plans and figure out which one is right or which one is the best based on the data that we have. The kind of transformations or the kind of decisions that we need to look at in this phase, in the cost-based optimization phase, have to do with join order, again, which one is joined first, the join algorithms, nested loop join or hash join or merge join, and so on. Aggregation algorithms, like we've talked about before, hash-based aggregation or sort-based aggregation. Again, these are things that we need to look at the cost to understand which one is better. Access path selection, how do we actually read the data from a table? Do we use table scan, like just a sequential scan, or do we have an index that we can use? So we can use an index scan. We could also have multiple indexes. So which one of these do we want to use? Because each of them may have a different cost as well. We could have also like a B-tree index or a hash index or multiple B-tree indexes on different columns. Each of them may have a different cost. So this is another decision that we need to make. If we have sorting operation, what sort algorithm do we want to use? Do we want to use quicksort? Do we have other sorting algorithms that we want to use? Each of them will have a different cost, etc. So these are all the things that we need to compare during that cost-based phase. And like I said, the new generated plans, we don't know which one of them is better until we start looking at the costs. Let's see an example of that to see how can a plan be better sometimes, but not all the time. Suppose we have a query like this, so we're selecting name from table employee where salary is greater than 300. Let's suppose that this is the table pages, just the employee table. These are the rows. They are stored in, let's say, 4 pages in this case. Now, suppose we also have an index on the salary column, right? Just a regular B-tree index. It's a non-clustered index, so the data is not sorted. And we know that in the index, in all the leaf nodes, we have row IDs or pointers pointing at where the data is actually located in the data pages. So the representation will look something like this. Okay, now to answer this query, what are the plans that we might possibly use? One plan could be do a table scan on the employees table. So just do a full sequential scan, get all the rows for each row, apply this filter, see if it's satisfied or not. And then for the ones that satisfy the filter, project the name column. So this is a basic table scan followed by filter followed by projection. Another potential plan, since we are looking for the salary value and we have an index on that, so we might use the index. So we can do an index scan with that condition, and then once we know the rows, we have to read them from the data pages and then project the name attribute. So these are two possible plans. Which one of these is better? Just looking at the two plans, we don't know. Either one could be better. Really, like, isn't always the index scan better than the table scan? We've said before that table scan is super bad because it has to do a full scan of the table, right? Is there any instance where the table scan is actually better? Let's see. Okay, we're looking for the value 3000, right? This value, if you look at the index, let's say 3000 is found at this part of the index. If that's the case, the query cares about salary greater than 3000. So if 3000 is there, this is the part of the index that we care about for this query. So this means we're going to scan only 2 pages. So once we find the index, we're going to follow the pointers back to the data pages. We're going to scan 2 pages, right? In this case, this is better than the table scan because the table scan is going to scan 4 pages. So scanning only 2 pages is much better. So the index scan here is the better plan. But suppose the 300 was actually found there, like near the beginning of the index. The data might be different, right? Like the data might be so that 300 is there and we have lots of other values after that. 3000, I mean. If that's the case, then this is the part that the query will read, right? And we're going to follow each of these pointers to read the corresponding page. We'll probably end up reading all the pages anyway. Plus, because we're doing random search here, not sequential, we might read the same page multiple times. The same page might be evicted from memory and then brought into memory again. So the cost of reading here is actually worse than doing a full table scan. Full table scan, you're doing a sequential scan, reading each page once, and you're done. Here we might actually read more than what we do in a sequential scan. So in this case, the sequential scan or the table scan is better than the index scan. So we can see that the same query, 2 plans, each plan might be different depending on the data that we have. So that's why we need to understand the data and understand the cost. So how does the optimizer estimate the cost? It uses something called a cost model. So the cost model means that for each physical operation, we have a cost function that estimates the cost of that operation. And that cost includes things like, the I/O, memory, CPU, and many other factors. Like in the beginning of this video, we had this simple example where I used the I/O, the number of pages read, as the cost estimation. Of course, A real cost estimation model or a real cost model will include lots more factors than just the I/O. So each operation will have this cost function to estimate its cost, and usually the input, or like this is a function of the number of input rows to that operation. So depending on how many rows are coming or how many pages are coming into that operation, this will give us a cost estimate for that particular node. We use the database statistics because that will tell us how much data we have in each table. And then we do cardinality estimation, or trying to estimate the number of output rows at every node in the tree, in the plan, right? So this is called cardinality estimation. This is something that has a lot of research done on it, and this is something that probably requires its own video, so we're not going to get into that in this video. I might have a separate video on cardinality estimation and database statistics, but for now, basically, you need to know that we have this cost model, we have these cost functions that depend on the input size, and it will give us a cost value or cost estimate for every operation. Now, the optimizer doesn't just create all the plan alternatives, all the plans from top to bottom, and then start estimating the costs. Usually what happens is that it creates subplans, smaller parts of the query, equivalent plans for that part, estimate the costs, figure out what is the best plan for that part of the query, and then try to generate plans for a bigger part and a bigger part, and so on. This can be done in one of two ways, either a bottom-up approach or a top-down approach. Let's talk about each of them to try to understand the difference. Let's start first with the bottom-up optimization approach. We call this bottom-up because we start small and then go bigger. We try by enumerating subplans that involve one table. So if you have a query joining tables A, B, and C, we try to figure out, okay, what is the best plan to just read the data from table A? What is the best plan to read the data from table B? What is the best plan to read data from table C? And then we go on two tables. What is the best plan to combine A and B? What is the best plan to combine B and C? And then we go to three tables. What is the best plan to combine A, B, and C? And so on until we get the best plan that covers all the tables and the query. So that's why we call it a bottom-up approach. At each level, we try to find the best plan that will give us that particular subset of tables, and then we use that in the higher level. So if we find the best plan that gives us table A, then we use that when we're trying to figure out what is the best plan to get A and B, for example, and so on and so forth. Let's see that in an example to understand better what I'm talking about. Suppose we have a query like this. It selects star from A, B, and C. So we're joining those three tables. We have a join condition between A and B and a join condition between B and C. And then we have another additional filter on table A. So as we said, we're going to try to estimate the best plan to read from table A, the best plan to read from table B, table C, and then the best plan that combines table A and B, best plan for B and C, the best plan for A and C, and then finally the best plan for A, B, and C, which covers the whole query. So let's start with the first one. We want the best plan to read from table A alone. One simple plan would be do a table scan on table A, then do the selection with the filter that we have here in the query. Easy plan, this is the default, right? Suppose we also have an index on this attribute A, right? So then we can do an index scan on this attribute with the condition that we have in the query. So now we have two different plans that we can use. Both will return the same thing. We can estimate the cost for each of these plans using the cost model. And now that we have the cost estimates, we're going to say, okay, given these cost estimates, this plan, the index scan, is better. So now that we've decided that, we're going to record that saying, okay, for table A, this is the best plan and this is the cost that we have estimated. All good? We can move on to the next one. Go to plan B. For table B, let's say the only option that we have is a table scan. We don't have any filters, we don't have any indexes, so that's the only thing we can do is just do a full table scan on B, and this is the cost. So we're going to record that as well. Same thing for table C. We only have a table scan, and this is the cost. Now we go to try to find the pairs, A and B. For A and B, let's say one potential plan would be do a nested loop join. where A is on the outer side and B is on the inner side, and we can estimate the cost of that. We can also do the opposite. We can have B on the outer side and A on the inner side, and we can estimate the cost of that as well. And in order to estimate the cost of that, we use the cost for the best plan for A and the cost for the best plan for B. We already have those. And then based on that, we can estimate the cost of the join. Assuming that we also know, or we did our cardinality estimation and we know how many rows are coming out of A and how many rows are coming out of B. So we have these two potential plans. We also have other, alternatives where we use hash join with A and B, or with B and A. We can also do a merge join with A and B, merge join with B and A. So we have all these different alternatives that will give us the same results, and we have an estimated cost for each of them. And let's say in this case, we're going to say that the best one that we found based on the cost is that second plan that has nested loop join between B and A. So we're going to record that as well, and then move on to the next one. So B and C, we're going to also say that we found the best plan is a hash join between B and C, and this is the cost. A and C, in this particular case, we don't have a join condition between A and C, right? So we're going to say that we're never going to use A and C because we don't have a join condition, because basically the best plan here would be a Cartesian product. Cartesian product is one of the worst operations because it just gets all the different combinations. So we're not going to use that in this case. Potentially we could record it and say that the only thing we can do is a Cartesian product. I'm just going to skip this for now. And then we go to the A, B, and C level. So now the options that we have are nested loop join between AB on one side and C on the other side. And when we say AB on one side, meaning the best plan for AB, which we have discovered before. So we can estimate the cost for that. We can also do BC on one side and A on the other side. So that's another alternative for nested loop join. Same thing we can do for hash join with all the different combinations. Same thing for merge join with all the different combinations. And again, we can estimate the cost for each one of those. Let's say with all of that, we decided that the best one was nested loop join with BC on one side and A on the other side. So now that we found all of this, we can start building the final plan. So starting from A, B, and C, this is the best plan is nested loop join, BC on one side and A on one side. Okay, so what is the best plan for B and C? We already have that. That's the hash join with B on the outer side and C on the inner side. Okay, so what's the best plan for B? That's a table scan. The best plan for C is also a table scan. The best plan for A, that was the index scan. So now we have the full plan, and we can just take that to the execution engine and run it. So this is the bottom-up approach. As we can see, this is simple to implement because it just iterates over the subplans with one table, subplans with two tables, subplans with three tables, and so on. It's very straightforward. One potential issue with this approach is that it's not easy to start considering some constraints about, let's say, the order of the data or what columns we want to output. For example, let's say we want the data, like if a query has an order by X, right? How do you specify that in the cases that we were considering? Instead of saying, okay, we want just the best plan for table A, we might want to split that into two different categories. We want the best plan for table A that is unsorted, and we want the best plan for table A that is sorted by X. So we might have more categories to consider based on if we have sort orders or if we have other specific properties or constraints that we're looking for. So that might get the algorithm a little bit more complicated once we start doing that. A lot of the systems that have this approach, they already have that implemented in them, but that obviously, again, complicates the algorithm. Another downside is that this approach, usually, it works only with what we call left deep trees. Left deep trees look like this. Usually you combine, like specifically with joins, you combine, let's say, two tables, and then you join with the third table, and then you join with the fourth table, and then the fifth table, and so on. So every time you add just one table, so the tree looks like it's deep on one side, which is the left side. So it will never get us a bushy tree like we have here in this figure, a bushy tree that may have multiple, like join A and B, and then join C and D, and then combine the results, for example. You will not get this from the bottom-up optimization, or at least most systems that implement this kind of optimizer. Why? Because, like we said before, the optimizer tries to limit the subset of plans that it considers. And one way of limiting that is saying, I will only consider plans that look like this, like a deep left deep tree. I will not consider any other shape of plans. This will limit the amount of plans that it considers, but it will also decrease the amount of time that the optimizer will have to take to come up with a final plan. So this is a constraint that many of these optimizers that adopt the bottom-up approach, many of them have that constraint. Which systems use this approach? This was invented in something called System R that was invented by IBM, and this got incorporated into the DB2 system, which is built by IBM. This is also used in MySQL, it's used in Postgres, and many other open source systems. Now let's talk about the other approach. The other approach is slightly more complex and slightly more difficult to explain, but I will try to simplify it and talk about just enough of it to understand what it's talking about, but I will not get very deep into the details in this video. The idea for the top-down approach is that we're starting with a logical plan, right? This is the logical plan that we have after doing all the heuristic rule-based optimizations. So we still have a logical plan. That logical plan is a complete plan. We start applying more transformation rules on this plan. These transformation rules will generate more alternatives and also start generating physical operations or physical plan. Once we have these alternatives, then we can start estimating the costs of each of these alternatives and then comparing the cheapest alternative. So example, just a small query on two tables joined on the X attribute. We also have an order by in this case. So let's say that the plan that we're starting with is a join between A and B with a sort operation on top of that. Okay, one transformation will say, take this join and generate the actual physical joins. So it will look something like this. So you have a nested loop join, or you could have a hash join. So using any of these with the same inputs will generate the same results. So these are alternative plans kind of packed into a neat little structure. Another thing would say, okay, we actually want the output to be sorted by X. And X also happens to be the join key. So we have a kind of join that actually produces the data in that order. We could use a merge join. So we could potentially sort the inputs on X and then do a merge join between them, which guarantees that the output is going to be sorted by X as well. So adding two sorts on top of A and top of B, and then a merge join on top of that, which will produce also the same output. So this is an alternative plan. One might say, hey, by the way, we also happen to have a clustered index on column X in table B. So if I have a clustered index by column X, it means that the data in table B is actually already sorted by X. So this means I can actually use that clustered index right away instead of having to do a sort on top of a table scan. And this will give us the same equivalent. So this can be used as an input to the merge join right away. So this is another alternative plan that we can use here. So all of these alternatives are generated using transformations. We keep accumulating them. And then we can start estimating the costs going from the leaves all the way to the top and trying to figure out, okay, which plan has which of these alternatives has the least cost and use that as the final plan. Again, this is a very simplified explanation of that algorithm. It has a lot more to it, but I don't want to get into this because the video is going to get much, much longer if I do. All right, so the top-down optimization, as we have seen, sort order, output columns, etc., are an essential part of the algorithm. If you want to sort order, you add a sort operation, and you can take that into account while you're generating different plans and so on. Same thing, like if there's a projection, you will take that into account as well as you're generating the alternative plans. Any other constraint are an essential part of the algorithm. This will give us more plan alternatives than we have during the bottom-up approach. Because again, this considers all sorts of things, like we have these transformation rules that just generate more and more options, so we have more plans. Of course, the flip side of that is that the algorithm is more complex. It's not as straightforward as the bottom-up approach. What systems use this approach? This approach was actually invented or originally published as the Volcano framework, which was also upgraded to the Cascades framework. It's an extension of the Volcano framework. This is used in SQL Server, and it's also used in the Green Plum database in the Orca optimizer. So I know this was a lot of information, so let's take a deep breath and try to summarize what we talked about today. Again, today I have talked about the query optimizer. This was an overview. I know there was some details in there, but I hope that it was not too overwhelming. First thing we talked about is why do we need the optimizer, right? And as we mentioned, because SQL is a declarative language, it doesn't tell us what are the order of the operations. So we have to come up with an execution plan. And there are many execution plans that can have the same result, that can answer the query that we have. Each of these plans may have a completely different cost. One of them may run in 5 seconds, another may run in an hour, another may run in 2 days, depending on the data that we have. So it's imperative that we have something that can find or identify the best plan and use that to run the query. This is where the optimizer comes in. The optimizer's responsibilities is to enumerate the plans, find out all the or most of the equivalent plans, or at least a subset that includes the best possible plans, and then compare these plans and come up with the best one. Comparing the plans can be done through the heuristic rule-based optimization by trying to eliminate the obvious bad ones as early as possible. And then we can also do the cost-based optimization where it tries to estimate the cost and use that to identify the best plan. Cost estimation happens by using a cost model, which means that each physical operation has a cost function that can use to estimate the cost of that operation based on database statistics as well as cardinality estimation methods, which we have not again talked about in this video. To estimate the cost and to enumerate the plans, optimizers use either a top-down approach or a bottom-up approach, and we have talked about each of those approaches and how it works in general. So yeah, this is in a nutshell how the optimizer works. The query optimizer is generally considered one of the most pieces of a query engine or of the database system in general. It is something that most people don't really understand very well unless you are someone who works inside the optimizer. So this is something that we cannot cover all in a single video. So I try to give an overview of how it works, and I hope that this demystifies the optimizer a little bit and makes it a little bit easier to understand. But there's a lot more to cover than what we've talked about today. I do plan on having one or more dedicated videos about database statistics and how they are used to estimate cardinalities as part of the cost model. There's a lot also that goes into that topic. There's a lot of research there. There's a lot of caveats there. So I definitely plan to talk about that. But please let me know what other parts of the optimizer you would want to hear about. Either it's something that we've talked about today or potentially something that we have not even mentioned today. Examples like, do you want to know more about the details of bottom-up or top-down optimizations? Other things that we may do is some of the advanced optimization techniques that are used for stuff like nested subqueries or CTEs, which is common table expressions, or materialized views, or any of the other advanced SQL structures. So we could also talk about those. But yeah, let me know if there's anything specific that you would like to see, or if you have any questions about what we've talked about today. If anything is not clear enough or something may need more explanation, I will be happy to answer that if you put it in the comments, or I may end up making another video if I see lots of questions about any particular topic. So please let me know what questions you may have or what areas you may want me to talk about more. Other than that, if you like the video, please hit the like button, subscribe to the channel to get all the updates. And with that, thank you so much for watching. Thank you for sticking with this long video, and I will see you in the next video.